Hello, my name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki has registered more than 300,000 members. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled, What to Consider When Architecting Your Next SoC, Architectural Trade-Offs, IP Selection, and Ecosystem Realities. The speakers today are Paul Martin, Global Director of SoC Architecture at Aion Silicon, and Darren Jones, Distinguished Engineer and Solutions Architect at Andes Technology. This is a live webinar, so if you have questions, put them in the chat box and we will respond to them during the Q&A. And you'll get a replay to the webinar after we complete this. Okay, ready to get started. Over to you, Paul.
Okay, so the topics we're going to cover today are not about how to use your PC, which you'll be glad to know. We're going to cover SoC architecture and why it matters more now than ever. We're going to look at some of the real-world architectural processes that we use in order to arrive at a realistic architecture, and some of the trade-offs that we'll actually undertake in order to get there. I'm going to show you a little bit about performance modeling and how we use performance modeling to optimize the candidate architectures that we're working with, and how we can basically get the right configuration of our design to deliver against the requirements, and also basically to give us some flexibility that we can actually adapt to requirements as the requirements evolve through the design process. Then we'll talk about IP analysis and vendor selection considerations. That's why I've got Darren here. Darren and I, obviously, Darren's one of our IP providers at Aion, and we work very closely together. And then we'll talk about the impact of ecosystem, its maturity, and some of the partnership strategies we can use to mitigate some of the issues we might run into here, and then conclude with a Q&A. So why is it that SoC architecture matters now more than ever? Well, we're dealing with very dynamic markets with varying requirements. We're in the era of AI, and obviously the innovation that's going on in that space is driving processing requirements, which we're expected to support on our SoCs. We're a victim of our own success. The more performant the hardware is, the more our software colleagues want to take advantage of the processing, and therefore the demand keeps increasing. Because we're dealing with that evolving environment, our designs that we start on day one need to be relevant in the market in several years. So we need to ensure that basically we've built in enough flexibility to make sure that we can absorb those evolving needs or risk of obsolescence in the market. We also need to deal with commercial constraints. Cost of silicon prototyping is actually a little bit prohibitive on some of the most advanced nodes. We find that cost of fabrication of a prototype device is now actually almost as expensive as a full production mass set. If we miss our market windows, so we have to hit our schedules, we can lose sales. Bottom line is we're really, right first time is really of paramount importance these days. I sometimes change that to good enough. Basically, good enough first time, because we basically may not be able to hit all of the targets, but we may be able to have suitable compromise that allows us to produce a useful design. Then we have the ecosystem maturity. We need to take this into consideration if we are going to target the most bleeding edge standards, the most bleeding edge process technologies. That's all going to add risk. So we need to look at this and take this into account when we're deciding on how we're going to implement our design. Software ecosystem, of course, is absolute paramount. We need to know what software is available to us when we start, and what will become available from third parties along the way.
So I want to add a little bit to what Paul is saying here, is that, the sort of the good old days 10 years ago or 15 years ago, where you could kind of slap a CPU, a memory controller, PCIe, and an interconnect together into a successful chip. Frankly, it used to be easier. It's really difficult now, and you can't just come out of the box with something that looks like the thing last year. So the SoC architecture is really key for a successful project.
Absolutely. Okay, so why is it that making decisions about SoC architecture on these large-scale SoCs is very difficult? Why is it hard? Well, we have ever more software functionality that we need to support. It's tightly coupled to, it has to be tightly coupled to hardware in order to deliver those software functions in an optimal way. When we're looking at our system requirements, the use case and the system requirements obviously are absolutely key for our understanding of what it is we're trying to do. But when we start out on the process, often those things are very imprecise. There's a lot of unknowns. Our application is highly dependent on software, which means we need to consider that at an early stage. But again, we don't often have the software, so the behavior of it lacks a lot of certainty, and we need to find a way to deal with that. Then we have performance, power and cost trade-offs, or what you might call functionality per watt per dollar. We have to build that into the process. It will put constraints on what we can do. And then there's the very obvious commercial constraints in terms of schedule to production, design, IP costs, mass costs, the cost of bringing production up, and then the unit cost as we go through the product life cycle.
So maybe just one other thing that I wanted to add here is that, again, it kind of goes back to my previous comment about, the old days used to be easier. It used to be that as long as you had a higher MIPS or a higher performance CPU in the next generation, you could always just rely on the software guys. They love it, they use it. But the way hardware delivers performance now makes it harder for software. We tend to deliver performance with more cores. And you have a wide variety of cores. There's low power efficiency cores and there's super high performance cores, but they use power. So sometimes you want to shut them off. This makes it difficult for software. So you really have to do hardware and software architecture up front. I agree, Paul.
Thanks. Okay, so being engineers, the way we deal with this is by having a good process that we can rely on. And this is an example of how we go about it at Aion. Essentially, we consider architecture development as a project, and that project has two very distinct phases. There's a requirements and use case analysis phase and a concept development phase. When we talk about requirements and use case analysis, obviously we want to actually understand as much as we can about the function of our design. What are the fundamental functions that drive the key parameters in terms of performance, power, and the cost of that design. We want to understand the data flows and how the different functions, basically, what are the dependencies between those functions. And very importantly, we want to be able to actually define a set of key performance indicators that we can measure the success of our design against. So that's kind of the first step. There's then a lot of engineering that goes on basically to develop that into a first cut of the architecture. There are usually multiple candidates. We will basically explore different IP options, different processing options in order to deliver the various workloads in the software. This is where our partnerships with our IP providers really is important. We need to be able to get either benchmark data or we need to be able to find ways to exercise some representative software from which we can extract some data about the performance of the cores that we're potentially going to use that's relevant to our specific workload. So we're really looking at what are the worst case functions that are going to drive, basically whether we're able to hit those key parameters. So the kind of the inner loops of the software is what we're really interested in here. So we may not have the full application, but we can get something representative that we can use to get some metrics from. The output of this particular phase is a kind of an initial cut at the architectural specification. It will have all the things you'd expect to see in that specification in terms of function, but it will also basically have the IP list and some of the candidate components that we're going to use. And it'll also basically give us an indication of the target process technology that we're going to use. By this time, there are a number of things we'll have assessed, which will have driven us to a particular target process, and I'll come back to that shortly. Once we've gone through that initial requirements and use case analysis step, and we have that initial concept architecture to work with, we then go into a more detailed phase, concept development, developing that architectural concept into a spec that the design team can work from. Now, this generally means we have to get down to the detail of actually modeling our system and verifying that the candidate architecture we've selected will actually meet the KPIs we've set. And I'll come back to that on a later slide. Any comments, Darren?
No, just that I agree. And you guys, I think, Paul, we can see that a lot of work goes in even before the output of this is kind of the architecture spec, right? Mm-hmm. So there's a lot of thought that's happening beforehand, and for the same reasons that you previously mentioned. This is actually the most important part where you can actually impact the ultimate delivered performance.
Yep, absolutely. This is why we really invest in this phase. It's something that is critical to the success of the project.
So for some of you out there, either who may have been doing this for many years, this is probably a little bit new, the emphasis on this front end stuff, or if you're brand new to, large SoCs, you may not have realized that you really do need to think about all this. And of course, some of you guys know this already, but if you can't, your company should be doing this, or at least thinking about it, or knowing your initial requirements, and then working with a company like Aion to help refine it into an actual spec. Yeah.
Yep. Thanks, Darren. Okay, so we talked about a lot of the work you need to do up front, but you need a lot of information in order to get started. So what are those must-know constraints that you require? So I mentioned that we need to know as much about the application as we possibly can at this stage. And we need to be able to understand what the KPI values are, the process indicators that allow us to determine whether we've got a successful design. We need to know about the SoC level requirements, things like the I/O signals and the overall performance, power constraints. It says area here, but really we're talking about cost. So we're talking about what's the unit cost, that constraint that we have to work with. What are the project budget constraints, the timelines that we have to work with, any market constraints that we might need to know about, an understanding of the product life cycle. So how do the chip level volumes evolve over time once it goes to market? And then a critical one here is certification needs. We need to understand what standards we might need to comply with. For instance, if we need an automotive design that's going to be ISO 26262 compliant, that really needs to be considered right up front when you're architecting your chip. It's not something you're going to retrofit. So really needs to be thought about from day one. And then software ecosystem. Ultimately, we're developing a platform that's going to execute software. We really need to understand the state of play with the software that we're going to utilize here. And then the final point here is basically ensuring we have all the development platforms that we need. And we need those from our ecosystem partners, from EDA vendors, but also our IP providers, so that we can actually model and evaluate our design. Okay. So you can imagine that leads to huge possibilities, and we need to constrain the problem somehow. So one of the ways we've done this at Aion in particular, and this is only one way, but this way kind of works for us, is we've developed an architectural framework. Has enough kind of flexibility in it that it can be mapped onto most of the designs that we work with. But what it gives us is basically a really solid starting point. We've captured basically all of the various compute elements as subsystems, and we have basically a subsystem for different types of processor architecture. They're based on a lot of our favorite IP, if you like, and we can generally scale up or scale out these particular compute subsystems depending on what we need. Then we have a chassis. The chassis itself provides essentially the fabric and the memory elements, but also some supporting services that we just need in order to get this design to function. So there's a system management subsystem that takes care of things like the boot mechanisms, may provide some of the security features, may even engage in some of the power management, switching power modes. Then we have subsystems to take care of the system I/O, how we get data in and data out of the system. And if we need it, there's an optional safety island here that we could incorporate if we have an automotive design. And that's designed specifically to ensure we can meet specific safety integrity levels. If anybody knows about automotive that's listening, I'm sure there is. We normally design this one to ASIL D. So what are the key trade-offs we can make here? Well, I did mention the fact that one of the things we can do is we can actually take some of the design and implement that in custom hardware. Generally, we find that tends to be around where we have specific sensors we want to support, maybe cameras, or this is or maybe a radar feed. We can generally do that in more efficiently in hardware than we can in software, so we might need some custom hardware there. So that's one trade-off. Then there's the general structure of the architecture in terms of how we can implement various functions. Can we implement using parallel processing or a pipelining architecture? We kind of build that in around this framework. Then importantly, and people kind of underestimate this, the design is going to need a bunch of process-specific hard macro IP. Particularly, I'm looking around the IOs, the PHYs that we might need. High-speed data converters are another one. Specialist memories. The point here is that not all of these components are available on every process technology. PHYs tend to be developed according to the latest standard that's prevailing at the time they're implemented on the most advanced process node that's actually available at the time. It's rare that you'll see new standards retrofitted to some of the older process technologies. So this is actually a thing we really need to consider is basically, will we have all of the IP available to us? And if it isn't, is there another way we can address this on a more mature process node? So there's a lot of thought that goes in around here in terms of IP selection in order to be able to determine the process technology, and obviously that also has a massive impact on cost. If we're on the most bleeding edge technology, then we're also using the most bleeding edge high cost processes. Digital IP, I'll talk a little bit more about how we select processors, memory controllers, and other soft IP. We tend to use the ones that we know best. And that again mitigates some of the risks associated with the design, and those are kind of incorporated into the framework. Other process technology drivers. Again, it's basically aligning the metal stack very often to those PHYs, what they require. But then we need to consider, do we need non-volatile memory or other specific specialized process options to support some of those hard macros, which are generally for custom designs. Okay, so this is kind of how we constrain things and get a head start on the design.
So as you guys can see, it's complicated. I mean, the point of this slide is there's a lot. So I would just recommend, think about for your system or for your company, what's your secret sauce? What's your differentiating factor? If it's hardware, make sure that that hardware unit, can do what it needs to do. If it's software, make sure you have, the processing capability so that your software can run.
Thanks. Yeah, I mean, I think the other point here is that we have a lot of data around these components that exist in this framework, which actually allows us to perform the analysis of the design very, very effectively. Okay, we said, how do we select a processor architecture? Well, I've kind of got four fairly high-level categories here. Very often we run into hybrids, but generally it breaks down into general purpose CPU. And that's the one we all know and love, I guess. It's a scalar core. It generally executes single instruction with a single data set. So for instance, it can basically execute A plus B, and then the next cycle it would implement C plus D, and then D plus E, all of those sequentially. The advantages of it is generally these have very broad instruction sets, and they can handle pretty much any kind of workload, just not necessarily in the most efficient way. What we've seen with modern CPUs is they're usually extended in some way, and you would add some capability to support SIMD instructions, something more like some of the vector processors that we see, but other kinds of accelerators are also get incorporated into these units in order to extend their reach. Then we talk about digital signal processors. It's another kind of specialized scalar core. Really, the instruction set here is optimized for specific maths for particular applications. One of the big advantages here is we generally have the ability to access different memory locations concurrently. That reduces the number of loads and stores we need to do back to the main memory, so it helps in the efficiency and there's also in the power management. Then the vector units, these are massively multi-threaded, and we're seeing these becoming more and more prevalent, generally tied to one of the general purpose CPUs, a scalar unit, which is really used to manage how these vector processors work. They're pretty simple, but they essentially execute an instruction across multiple data sets. So I gave the example of the scalar processor, A plus B, then C plus D. This would actually execute A plus B, C plus D, D plus E. All of those would be done concurrently in a single cycle. And generally we can do very wide data. So it's very efficient for processing through large blocks of data, performing simple operations, numerical operations on that data set very quickly. To do that, it generally has a local vector memory to store that data so that it can efficiently access the data in the right format. However, it's not very good at actually navigating its way around that memory. It doesn't have any ability for conditional execution unless you actually augment it with some additional memory management technology. And that's actually what we're seeing a lot right now, because as we want to use this kind of vector processing capability to process things like AI models that are based on transformers, those are based on 2D matrix multiplication. Data basically isn't really, it wouldn't typically be stored in a way that would be very helpful to a vector processor. So that's where it kind of needs some help with some additional memory management. So that's an option. And then we have GPUs. GPUs being massively parallel multi-threaded cores, really good at handling lots of parallel workloads which have lots of parallelism, where basically they're operating on the same shared memory. But that comes at a cost. Basically, it's really at the expense of efficiency, generally in terms of power or die area. They also require specialist ways of programming them, so you need to think about the software environment that's going to support a GPU. So those are kind of the options. So this is where it's really imperative to understand your workload and the kind of workloads you're dealing with. If you remember, I talked about what's the worst case function we need to support that's going to impact our ability to hit performance. Generally, what we're looking for is those kind of functions within the software, and understanding which is the appropriate architecture that we're going to use to actually implement those functions. Okay. Do you have something to add, Darren?
No, but it's a good lead in to the next slide, which I will talk about, I think.
Okay.
So once you've sort of decided kind of, okay, I want a general purpose CPU, or I want a DSP or vector unit or whatever it is, how do you pick which one? And I've kind of divided it up here. And if your team leans more towards hardware, don't forget about software. If your team is more of a software-ish team, don't forget about hardware. So, I think people know that they want to look up, PPA, performance, power, and area, but you also need to think about, is it going to fit into my system? And do I have an AXI-based system, or do I need something different? One thing that's easy to forget is, can I configure? For soft IP, there's usually a lot of configurability, and do you have the right configurability that you need for your system? Or if you want to go with hard IP, don't forget, for instance, in a processor, you then cannot configure it. You may not be able to customize it, add custom instructions or a coprocessor interface. You guys can read the software considerations here. Sometimes there's always a make versus buy decision here. What software are we developing ourselves? What can I go out and get in terms of libraries? And it varies. So these are things you need to think about as well. And then there's kind of, you get down to the nuts and bolts. Is your IP provider gonna give you all the stuff that you need? RTL is obviously there, but how is their data sheet? How is their documentation? You don't have to read the whole 500-page thing, but pick some sections that are important to you or that you're knowledgeable on. Read it, see if it's well written. Do they provide the right models? as Paul's talked about, modeling your system is absolutely key. So you want to be able to do that even before you have silicon, and ideally, maybe even before you've chosen your IP vendor, so that you can run some benchmarks, perhaps your own benchmarks. If you can get access to product support, send them in a couple of questions, see how well they respond. And then don't forget about some of the more soft requirements, like is that IP been seen in silicon by somebody else? Your IP vendor probably won't tell you who, but they can confirm if it's in silicon or not. And once it's in silicon, that's a huge positive. And then of course you can also go with the vendor reputation. And by that, I don't mean Googling around. That means contacting people that you trust, who have dealt with that company before, see how they felt was the support, how was the quality of the deliverables and the IP.
Okay.
Yep.
Thanks. So I talked about modeling, and this is something that kind of the approach that we use in Aion, and essentially what we try to do is we try to build a cycle-based system model of our chip. And what that basically means is that it's cycle accurate, but we're essentially just running a fairly loosely timed transaction level model, which we've annotated, instrumented with timing. It's based on a custom workflow that we have, but it's built on top of a commercially available System C modeling environment. So this is something other people could explore. What we have done is develop a series of transactors which allow us to where you can program the traffic profile that actually we expect to come from each of those processing elements, so that we can exercise the fabric and the all the way down to the main memory. We can also incorporate each of the I/O devices, whether master or slave, and we can enhance the model should we want to include things like local buffering and things like that. So it actually builds a good model of how traffic is actually going to go through our system, and basically highlighting any specific bottlenecks we might need to deal with. Within that environment, if we have accurate enough models of the fabric and the memory controllers, we can start to tune those and try to remove some of the bottlenecks that way. However, you'll probably want to know, how do we come up with the right processor configuration? I'll come back to that shortly. In terms of how we model traffic on the bus, I've just got it here in a table. Each row in the table represents a task that's being executed on a particular processing element. It describes initial reads that we need to do in order to execute that task. On the third row here, you can see there's an 8 kilobyte data block that we're going to process. We're going to move it in bursts of data. I'm going to read it in bursts of data here at 3096 bytes at a time. And we're going to do that every 3.5 microseconds. Okay, so it gives you an idea about how we model the traffic here. And then similarly, we define how we would write the result of that task back to memory, and we allocate some time for processing that particular function. And that's based on sort of benchmarking that we've already undertaken to understand the timing for those processes. Okay. So this is a more detailed explanation of how we might optimize a processor core within that modeling environment. So in this case, I've taken a DNN, an AI model, to show you how we kind of get to modeling the traffic and how we can close the loop with the configuration of that particular core. So generally speaking here, we're deeming an AI model. It might come from something like, in this case, it's an inference engine. So we're taking the model from something like TF Lite or ONX, and we're taking advantage of the fact here that the compiler understands aspects of the microarchitecture of the processor we're targeting, but it also goes through the compilation process in a two-step way. First step actually produces an intermediate representation of the code that's going to execute on the processor, and that's basically comprising all of the operations, all the functions that are going to be executed and converted to code that's going to be executed on the processor. We can extract from that intermediate representation a view of basically how that use case is constructed, and how it's built up from the various operations that it's going to perform. Against that, we can actually add timing. Again, we have benchmark data that allows us to know what to expect from the processor when it's processing each of those particular functions, each of those particular operations. So we get a timing model for the task that's executing on that processor, and we know that the form of the data that's basically being read and the data that's need to be written back. So this actually gives us something we can plug into the system model. We have similar models then for all the other processing elements, and we can describe the relationship between each of those tasks in terms of sequencing, even down to how we might pipeline some of those processes. So running the simulation, we can actually identify where the bottlenecks are. We can then come back to this particular compiler, and we can actually start to play with the microarchitecture and change how the compiler produces that intermediate representation of the code. That itself changes the form of the graph, and we'll get a different timing. So there's lots of things we can do here, depending on the type of processor that we're dealing with, but this is at a high level what we're doing in terms of shaping the graph, shaping the timing of the processes, and influencing how the data transits the system. Removing any potential bottlenecks and ensuring that we've got a performance system.
Yep, this is absolutely critical. It'll tell you things like, is my cache subsystem or my on-chip memory able to hold the working set of whatever my workload is? Because if it can, you'll get good performance. If it can't, performance falls off a cliff. Or if you're streaming data, can you support that number of outstanding transactions, through your interconnect? Things like that you will see in a simulation like this.
Yep, thanks, Darren. Okay, so let's move on a little bit and talk about the ecosystem realities. Reality of it as an architecture team, we need data from pretty much the entire supply chain, all the way from foundry, all the way up to the IP providers and everything in between. IP suppliers are critical to us at this stage. We need to ensure we have the correct IP selection. Get that wrong, we get a non-performant design, but equally we basically are investing a lot of money in those IP licenses, and we don't want to get that wrong. So it's really important that we partner with those IP suppliers, and we do that as proactively as possible. We want to make sure that we have the data available to us that we need before we actually set out on the journey through this architecture phase. Part of that proactive engagement means we have the ability to perhaps align roadmaps with the designs we're going to undertake, to align schedules, to know when we're going to get access to the IP that we need. We get access to the data so that we can build those architectural framework models up, things we use to analyze our design, and really to support us in making those right selections. There's a lot of stuff that we don't know about IP that comes from vendors. It's their technology, and it's important to get access to the right people. Another area that we've seen more recently is this ability to actually customize the IP, and obviously that's a feature of RISC-V. A lot of things are intrinsic to the kind of RISC-V processors that we receive in terms of the customization and the extensions we can support, but often things come up where we have to incorporate one or two additional tweaks in order to make some of these customizations fly, and that's where this collaboration really comes into effect. And then finally, we need reliable support. It's not so much a case of if, it's when things go wrong. And we really need to ensure that our partners that we work with have both the capability and the capacity to support us when that happens. What we don't want to do is be hit with a 6-month tape-out delay because we can't get the support or the updates that we need.
Yep, I think that's exactly right, and a perfect lead into this slide that, collaboration and partnerships, it's so difficult to build a successful SoC these days that you have to, it takes a village, so to speak. So here's a couple of, from my past experience, you want to collaborate with your IP vendors. So talk with them early on while you can still change things, things like, I'll give a simple example. If you know that you need floating point, but you only need 32-bit floating point, then can you configure the FPU in your IP to be 32-bit and not 64-bit, say? Because if you can, that's going to save you half the area of the FPU. So, you know, can you customize it in the way that you need? Also, I would just emphasize that all of those deliverables, things like I mentioned before, you know, those are going to help. So try to leverage all of that. If hopefully your IP provider sends a test bench, delivers a test bench, you know, run it. That's probably going to find the dumb mistakes, right? Their documentation, you know, read it. I get that it's 500 pages long. There's no way you can, you know, absorb it all in one reading, but it definitely helps. And utilize all of those different flavors of models that you've got. And maybe the other thing is, you know, utilize that support hotline or email. I don't, when I say contact them before you waste too much time, you know, you know, we get customers who they don't even try first. And so that's a little bit frustrating. Of course, you want to try to figure it out, but I've also got customers who spend a week going down the wrong path. And if they had only contacted us, we could have set them straight on day one. So, you know, if it's not obvious to you, call. That's what support is there for. And that allows you to build a relationship with those support engineers. So the more they know, the more they can help.
Yeah, great, thank you. So, you know, really other key takeaways, I guess, from the webinar, from an Aion perspective, also from Andy's perspective. So we talked about the fact that the SoC architecture is a very critical project effectively that occurs before we start implementing our RTL. The more investment we make in getting the architecture right, the more chance we've got of a successful design. We really need to make sure that the requirements and the use cases are defined as fully as possible. We know there's going to be some uncertainty. We know things are going to change, but we really need to get a full understanding of those requirements and use cases as early as possible. And once we have that, then we need to actually define what are the key performance indicators that we're targeting so that we know that we've achieved our goals. And we try to do that early on. We continually evaluate against the KPIs. We may even update the KPIs, but we always have something to actually measure our design against. Then we need to ensure that the software and hardware dependencies are analyzed, again, as early as possible. We're essentially developing a compute platform for software for most modern SoCs, and therefore there's a tight dependency, particularly as we have to produce much more optimal hardware to support the most advanced workloads. Then we're constraining the problem. We're constraining the problem by mapping it to an architecture framework, a framework where we have a lot of data about potential IP components and the ability to map our function onto that framework fairly quickly and evaluate the design. When we choose processor architectures, we're choosing a processor architecture based on the workload and really looking at the worst case functions within that workload that are going to really stress our processing capability, and choosing the appropriate architecture to handle those workloads and those worst case functions. When we have our initial architecture, we're going to model it and we're going to simulate it and basically refine that design, but through evaluation of the design, exercising it in that system level model to remove the bottlenecks. And we can do that iteratively. We can play with the design configuration, the IP configuration to make sure that we have an optimal design. It also allows us to adapt when requirements start to evolve. When we get new requirements, we can start to adapt the configuration of the design somewhat. Obviously, we want to keep it as stable as possible once we start to develop the design, but it does give us some ability to do that. Then the advice is use the most mature process technology and IP that will meet your spec. The closer you get to bleeding edge, a bit more risk you're going to encounter and the higher cost you're going to have to absorb. And then finally, you need to prioritize that ecosystem. Ensure you've got the right partners that you can trust and you can work with, work proactively with them, collaborate early on your design. Darren.
Yeah, so perhaps I'll maybe up level it just a little bit. You know, we've emphasized how important architecture is, and I think that's the takeaway I would like you guys to get is that the more time you spend up front thinking about architecture, modeling it as best you can, the less time you're going to have in making changes later on. And those changes are very expensive in terms of schedule. So you want to try to avoid that. Engage early and often with your IP providers, you know, especially if it's a processing provider, you know, decide what you need. And if you need to design something yourself, figure that out as early as possible, and treat your IP providers as partners and use them. That's what they're there for. They want you to succeed. So I'll just emphasize what Paul ended with is that collaboration is absolutely key. Yep.
Okay, thanks, Darren. I guess that's really at least the conclusion of the presentation, and you know, we're certainly in a point where we can take some questions if there's time. I just want to add that one of the things that Aion offers is a virtual workshop or an architecture design service. So if that's something you're interested in, if you're starting a new design, then by all means, please contact us. Darren, I guess that's pretty much the same with you, right?
Yep, sure. No, that's a great service. Paul and I have worked together on a few projects now.
Okay.
All right. Thank you, guys. We do have some questions, so let's get started. From software executing on the core to develop models for concept development, how do you build it very much in time? How detailed models of cores do you keep around?
So let me take a first crack at that. So, you know, in the olden days, you know, which I suppose isn't that long ago, we used to be able to build hardware and then kind of throw it over the wall to software. You cannot do that anymore these days. So there's always hardware software co-development. I think the closer you are to the hardware, or to the iron, as we say, the more cycle accurate you need. But if you're up at the application level, you probably don't need that. And the reason I say that is that the fastest simulation models will be the so-called instruction accurate models, things like QEMU. So, and you know, pretty much all of your processor and DSP providers will have a model for you, and that will run fast. Software guys like those models because they run fast. You can run actual workloads versus the cycle accurate models are slower. So maybe you can only do your inner loop for those, or if you're doing firmware development or very, you know, driver development, you might need something that's more accurate, but those tend not to be, you know, tens of thousands of instructions. So I would say start that software development early, use the model that's as fast as you can get, and live with a little bit of timing unknowns.
Okay. Another question, what about the new constraints like security, cost, configuration, and safety apart from normal PPA?
Well, that's an interesting one. Yeah, go on,
yeah,
Darren.
Go ahead, Paul.
Okay.
All right. So those are key requirements. Just, you know, Paul and I have sort of mentioned things like, you know, do you need a DSP? Do you need a vector unit? But we are seeing more and more that safety and security are also key things. So to me, it's, not to oversimplify, just another requirement. You need to make sure that your IP supports what you need. If you don't have the expertise and this is new to you and your marketing team is saying we absolutely need to have this, then, you know, work with your IP provider. They can probably help you understand what is needed there, you know, as simple as ECC all the way up to, you know, cryptography acceleration and root of trust, right?
Yeah. So just to add to that, I think when it comes to safety and security, the two things are very often linked. If you have a safety critical design, then security often comes into play here as well. interestingly enough, when we do talk to customers and say to them, okay, what are your security requirements? They go, yeah, we need some security. And then it's basically everybody knows we need to secure our design, but they really are not clear on what those requirements might be. Generally, the first thing we say is, okay, basically, what do you want to secure? Who do you want to secure it from? And then finally, how much do you want to spend? Because essentially, that's a limitation on what we can do. But essentially, we will develop a security architecture based on the requirements in terms of what it is we want to protect and how and what sort of threats we're trying to protect it from. There's a similar approach to safety. We're trying to understand what are the safety hazards in the design and how we can mitigate them. That has to be taken care of early on. It generally requires additional hardware. So I mentioned that safety island. That's typically a dual-core lockstep core that's being used to provide that ASIL-D functionality. So that's going to contribute to your die area. There may well be other structures in that design that we need to mitigate those safety hazards. Then we would run into the design cost of something like this. Basically, when you get into both security and particularly in safety, we need a very rigorous design process, and we need to really be able to fully verify our design, the verification work we need to do to demonstrate that all of those safety mechanisms actually achieve their goals does actually impact both the design cost and the schedule. So you have to prepare for all of that when you're working through your design. I guess there's a lot more I could say on the topic, but hopefully that covers the question.
Yeah, we have more questions, so we should move on. What do you think of the standard efforts like UCIe and CXL?
Oh, that's a controversial question, if I say so. So I actually do think that chiplets are kind of going to be a very successful future technology. However, I think it's frankly still in its infancy. Companies like Intel, AMD, and there's others who can control all of the chiplets and kind of align all of the IOs so that they're very optimal, today are successful. I think the idea, of having an interface which is a chiplet interface, we need to get there, but I'm not convinced that those things are quite there. So it's still a very rapidly evolving space. So it's not a solved problem. I would say absolutely it's the future. Focus a lot on those. How am I talking between chiplets? Because it's moving a lot.
Yeah, in fact, there's a follow-up question. What is your opinion on chiplet interconnect bottlenecks?
Well, I think it's hard, frankly, it's hard to say. You do have to design for that, like you design even if you just had a monolithic die. You're going to have potential bottlenecks, and you have to think about that. A chiplet to chiplet interface is going to necessarily be a lower bandwidth than something that was just on die, and you need to consider that, and that may drive your partitioning from, say, a compute chiplet to an IO chiplet, right? But if your IO chiplet has limited bandwidth, you don't need it to match the compute chiplet bandwidth because it's just going to get blocked anyway. So there's no easy answers here, right? It's you do have to think of the larger system. Yeah.
Okay.
Yeah, it's true, and you really need to understand. Again, it comes back to the data traffic that's flowing over that interface and how that basically interacts with the memory. So yeah, that's really key. Again, is to understand what that data traffic looks like. A CXL is actually an interesting one, but that's a slightly different problem to the chiplet issue. That's more about basically, how can we distribute processing over multiple processing elements, processors, and have them interact with a memory device, an external memory device, and ensure that basically all of those processors that are working together basically have the same view of memory. They all have local copies sitting in their caches, and we've got to basically find a way to make sure that we have coherent view of that memory. So CXL is useful in the sense that it puts some of the responsibility for managing that coherency back on the memory device. It knows when somebody is trying to update its memory, therefore it holds off all of the other hosts until that's done. It also tells them to basically invalidate their cache. So this is all useful stuff, but it's all very new, and how that works in practice and how it impacts the system is something that's quite difficult for us to get our minds around.
Okay, another question. My question is regarding automotive, which is very complex. It has at least 5 key modules and multiple sub-modules: powertrain, electronics, chassis, electronics, safety, security, etc., etc. So how would you create these subsystems, and would you lay out these blocks? Would you lay out these separate blocks, or would it be under CPU subsystems or question mark?
I'm not entirely sure I followed the question. So basically, we've got a design that has a lot of modules, which are taking sub-modules, which are taking care of different functions within the design.
Right.
So I'm assuming this is all on a single chip. Again, it's basically being able to understand what the workloads are that are basically supported on each of those subsystems. And what's the relationship between them? Is there some level of orchestration that needs to take place? So there's a lot of work going on in the software space right now to kind of take care of, these sorts of problems. I'm thinking of sort of initiatives like SoC, where essentially you're seeing much more sort of an approach to kind of containerized applications that are being dispatched from a central controller across multiple modules. But that's quite a complex software architecture. It's pretty bleeding edge. But it comes down to, how do you allocate function to those individual subsystems? What are the relationships between them? Are they sharing the same memory? Are they sharing similar resources? And basically, how do we understand the relationships in terms of data between those different blocks? But yeah, I mean, it's really trying to understand what the system problem is you're trying to solve, whether it's at the software level or the hardware level.
Yeah, we can address that through email. There's another question. Do any of the non-compute subsystems contain their own CPU cores?
Yes, and that's actually an interesting area. Things like some of the latest high-speed controllers, think PCIe, but really anything that is running at multi-gigahertz SerDes. There's a phase training that doesn't just happen in the beginning. It actually can have training phases that happen while it's live. That's very complex these days, and you'll see microcontrollers that are deeply embedded within. So when you buy, for instance, a CXL controller or a PCIe controller, it might very well have a microcontroller inside of it. That's one area where Andy's processors have been adopted, actually. But you don't have to worry about it because your CXL provider is gonna, basically say, here's the block, here's the software, and it's typically in a ROM or some other thing that you don't have to worry about.
Yeah, that would have been my comment as well. We don't have to worry about it because it's kind of under the hood.
Yeah, that's right.
Okay, another question. In the Aion framework, is it possible to write the software for each of the system level functions described by the different subsystems independently of each other or in parallel to reduce development time?
So yeah, for sure, we would expect the software to be developed concurrently with the hardware development here. As I mentioned, we start with whatever we know about the software functions and allocate them to each of those processing elements based on what we know about the functions that they need to support. What's the worst case? As the software starts to evolve and we learn more about it, then actually we can build a much more high fidelity model of the system. So that architectural framework and the modeling environment we have is designed to actually evolve all the way through the design process. So we may well have a virtual prototype that's running loosely timed programmer's view execution of the software, but concurrently we're developing the hardware to the point where we have RTL instantiated in a test bench environment. We can actually run real code to some degree, maybe on an emulator, or we may produce a prototyping environment like an FPGA environment. So yeah, but basically the two run concurrently, and we're basically trading off between software and hardware all the way through that process to make sure that we've got the right system.
Great. Well, there's more questions, but we'll have to answer these on email because we're out of time. Thank you, everyone, for participating in the SemiWiki webinar series, and have a great day.